Well, good evening, everyone. It is 9:39 p.m. up here in South Carolina. I suppose many of you who are seeing this are aware of a paper I've published uh, back in October 2025 and a subsequent presentation at the Florida Academy of Sciences in March of 2026 on a claimed analytical solution to the Navier-Stokes equations for cases of incompressible flow, simply connected domain, and all nine nonlinear terms unsimplified and left wholly general, with a few concluding remarks in the paper on the clay problem, which asks for infinite smoothness and square integrability over an infinite volume of space over an eternity of time, assuming your initial condition is also C infinity smooth and square integrable, specifically L2. I take it as L2. If I remember correctly, it's L2. The technical exact conditions could be stricter, but based on the square integrability criterion, I'm currently, my mind is jumping to an L2 Sobolev space, but it could be different. Without further ado, I'd like to say to everybody who took interest in that video and that paper, thank you very much. Thank you for your support, and thank you for your kindness in your. Honestly, it is. You don't know how much comments like "Holy guacamole," and and I'm glad you got it done or whatever. You have no idea how encouraging that is, because we're living in a world where most people don't care about math. They don't see its consequence, like how consequential and how beautiful math is, and how much engineers and physicists can use math, and even mathematicians can use. I mean, they always use math. That's kind of why they're called that. But we build new theorems off of existing ones. But I don't want to get too lost in the weeds here. I want to address something that I've seen develop in the course of the past few months, since early weeks. It's technically been about 1 month, maybe two. Yeah, about a month and a few weeks since the conference. Now, the video, a 15-minute video, is worth many 52-page papers, and it's going to get the information way further out there. Now, in this video, I'm not going to go into any deep diatribe of defense yet, anyway, about why I believe this math to be correct. I'm only going to point out that there has been a Redditor that has asked the question. This is really the only recorded public discourse on this preprint. In this video has been this Redditor who has published a Reddit post asking, "Did Florida Polytechnic University solve Navier-Stokes?" First off, I want to clear a few things up. Florida Polytechnic University, although it has been absolutely exemplary in its interest in helping me get this research out there, they have not contributed to the content of any of my papers. They have not contributed to the content of any of my conference recordings. None of my videos were. I received no assistance from Florida Polytechnic University because I did not need any. My tools the tools I use for my math research are completely open source. I use GNU Octave for scientific computing tasks, as well as SciPy with Python with Matplotlib. I use ParaView for a lot of my graphing and plotting tasks. And when I plot this solution, this purported solution, in the coming months, I'll be using a lot of Fortran. You can download all of these things for free. Wikipedia, thankfully, is still free. I hope it will always be free. The main monetary costs of this solution were purchasing these $300 3-inch thick copies of Polyanin and Zaitsev's compendiums of PDEs and ODEs. One on nonlinear PDEs, one on linear PDEs, one on ODEs, and one on integral equations. And that covers Fredholm, that covers Volterra, first kind, second kind, and a giant number of surprisingly large classes of nonlinear varieties of the same. I also found a copy of Eric Komke's Differentialgleichungen. I think I'm pronouncing that correctly. Correct me if those of you in Germany, correct me if I'm wrong. That's essentially a seminal text on ODEs covering second order linear, Riccati, Abel, even Keeney equations, which are just a generalization of Bernoulli, Riccati, and Abel. It's almost like I'm not going to say the ultimate ODE, but I'm going to say it's for all practical industry purposes. It often is, especially for control theory. Now back to this Reddit post. This Reddit post asked, did Florida Poly solve Navier-Stokes? Now they did mention me. The first reply was from an unidentified. I mean, it's always unidentified. It's Reddit. First reply said, no, he's an independent researcher, and his talk sounds like the type of AI slop that is commonly passed off as solutions to these kinds of millennium problems, or I paraphrased it, of course, but that's what I remember reading. Well, if I can offer a response to that, saying that I'm an independent researcher, which I am an independent researcher. I'm not, again, I say Florida Poly did not contribute to the content of my research. Therefore, even though they're my alma mater, they're my affiliation, the fact that no other person there or anywhere else contributed actively to the content of my research does technically make me an independent researcher. I'm not a professor. I don't have a graduate degree. My education in math is not formal. It's almost entirely self-taught outside of what I learned in undergrad in my degree in mechanical engineering. That gave me a basic grounding in calculus, differential equations, and various things, including fluid mechanics, heat transfer, thermodynamics, and Newtonian physics, and all that. I was unsatisfied by that, but I also did not want to sink more time in education when I could build myself a future in the industry. And I remain in the industry to this day, and I have no intention of returning to graduate school. At this time, I have no intention of going back to school. I love where I am in the industry, and I intend to stay there for the foreseeable future. I intend to stay there as long as I possibly can. I love real world things. I love things I can put my hands on. So I am independent as a researcher. But saying that it's AI slop, I think the discussion may have taken a turn into the ad hominem more than it's taken a turn into criticizing the actual mathematics. Another comment posted just 9 days ago, as of this recording, has said that it looks like a manic episode, referring to the paper and to the recording of the conference. Now, I understand that my conference recording was very, very fast. I spoke very quickly. And when I spoke very quickly there, that was because that was a rushed presentation. Now, I didn't tell anybody this, but that was actually a very rushed presentation. And if I had known that my speed of talking would get me called a manic, well, whatever that means, then I probably would have condensed the content of the presentation. So if anybody has actually thought that I'm insane or something because of this, I can assure you that presentation was very well thought out, according to a lot of people. Not me, but a lot of other people. Uh, I had my faculty mentor from Florida Poly say that my talk was quote unquote extraordinary. His words, not mine. And I would much rather take criticism from an established researcher who was a professor, a very well known one, than some Redditor. But the reason why I'm commenting on these Reddit posts is because I think the ad hominem attacks are. I think those are creating the risk that the discussion could be going too far towards uh, the man and not towards the mathematics. I think what would really help the discussion move forward, if I can offer some feedback on that, or if anything, would be to, if you're going to answer the question, did Florida Poly solve Navier-Stokes, or more specifically, did Alan Longfellow solve Navier-Stokes? Uh, Tear into that math. Open my paper, run that thing through 10618, for goodness sakes. Destroy it. Give it all the scrutiny you want to give it. That's what the scientific method is all about. I'm not saying say it's wrong for the sake of saying something is wrong, or say it's right for the sake of saying something is right, but I would rather you take the math to the test of merit. I'm aware that our society is becoming, in a lot of ways, is becoming less and less meritocratic by the minute. But that doesn't mean that we can't make math meritocratic. I think we need to steer the discussion away from the man and towards whether the math the man has published is true or not. And at this time, a lot of people in informal conversations have steered the discussion of this type of thing towards peer review. I want to clarify that this paper is a preprint. That means it's been published but has not yet been peer reviewed. In order to peer review this paper, I have to submit to a journal. Submitting it to a journal is a very messy process. I am very likely to get a desk rejection as it is. And the reason why is because journals are not used to seeing, they're not used to really, they're not used to seeing through purported millennium problem solutions unless it comes from a researcher that is so prolific that they kind of have to review it. Now, I'm not that prolific. I'm not that well known. So I'm kind of like a new guy in the scene. They're like, oh wait, who's this Alan Longfellow guy? So that's a lot of where we're at. Now, it's very likely I'm going to get this paper rejected by a large number of journals unless I can find someone that has enough faith in the structural integrity of my work in order to maybe vouch for me on the inside, or even review it themselves. Now, that might sound really that sounds really unethical, which is the reason why I really don't want to, I don't want to entertain that idea. That to me reeks of academic dishonesty. So I want to do it the honest way. I want to do it the real way, and that's what I really want to push for. Is if I'm going to get this thing peer reviewed, it's going to have to be done cleanly. I value trust and professionalism in everything I do, and I don't want any underhanded deals. I think that's very bad. I think that's the reason why. By Dr. Perelman, who dealt the final knockout punch to the Poincare conjecture, called such people vermin. People who are in the game for the perks, like they want status, they want to up their professional game, and they think math is just a tool to do that instead of a beautiful truth about the universe that can help us flourish as human beings. Those social climber types that are getting into math. I completely agree with Perelman, and like Perelman, that mentality is sometimes cost me. It sometimes cost me things I love in life. Like there's a lot of friends that are no longer friends, not because I hate them or they hate me, but because I simply value transparency in these types of situations. This is unfortunately not how a lot of academia is structured, if we're honest with each other. And for that reason, it's likely going to take me a lot of work to get this peer reviewed. And it's also a work that is large in its magnitude, in terms of, I'm sorry, its size. I think I'm too used to talking in vector terms. 52 pages is not really a journal article. It's actually what they would call a monograph. In fact, that's 52 pages on 8.5 by 11 paper. Now, if you were to shrink that down to like a 6 by 9, like Dover books on mathematics, they have a lot of 6 by 9s. If you were to shrink it down to a 6 by 9, it would fill about 120 to 130 pages. So this paper is less of a paper and more of a book, a small, short book on math. That's not something I can expect a journal to publish in their standard proceedings. That is going to require something very specialized, and I may even have to rewrite the manuscript in order to get it to fit into a journal. That is something I will do if it comes to this. But I think what I need to do right now is focus on plotting the formula. That's one thing I need to focus on. And the second thing I want to do to contribute to the discussion a bit more and move the discussion out of the YouTube comment section and out of Reddit and into something that has a bit more, something that's basically a bit more inclined towards mathematical dialogue more than phatic communication, just like social encouragement, which is wonderful, like I said, or ad hominem insults in the case of Reddit. So I think my next move here, the thing I'm going to do next year with regards to this purported Navier-Stokes solution, is to create a series of Khan Academy-like videos where I explain the math in depth. I'm not going to rattle things off like that conference, but it'll be slow, calm, and collected, same tone of voice I'm using here in this video. And I think that is going to help tremendously with helping others understand the math without having to sift through 52 pages of math speak. It would be better for me to, I believe in the old adage in many ways, if you can't explain it, you don't know it. So I think because it would take me, because my knowledge is limited, my knowledge of my own work is limited. I think 15 minutes is really like my limit with with how much I can fit, with how short I can make the explanation and still make it a full start to finish explanation. Now, so now I'll be recording a few tutorial videos on how to understand the process of solving it in this particular way. That's the next thing I want to say. So first thing I want to say is plots are one of the next steps. Second thing I want to say is tutorial videos are next. Third thing I want to say here is that the presentation covered the bounded flow case. I did not have enough time to do what I really wanted to do, and what a lot of people really want to see is the unbounded case, the clay case. This is where I want to get into a critical nuance about Navier-Stokes. There are really two large ways to understand Navier-Stokes, or really any PDE for that matter. On the one hand, you have how a mathematician would understand it, which has to do with what is the size and shape of the equivalence class of functions that are able to solve it given a defined set of initial conditions. And mathematicians don't think of this as, okay, it's only x squared, or it's only sine, or it's only exponential. No, they think in terms of a structure called a Sobolev space, which is basically a box you can draw around a function, a set all functions that have a certain type. If they're all square integrable, that's the Sobolev space L2. If you can take derivatives of them and derivatives of that and derivatives of that and keep going and going and going, taking derivatives of derivatives of derivatives all the way to infinite order. In other words, if derivatives of any order all exist in our well-defined, then we say that that is a C infinity function. That function is a member of the C infinity Sobolev space. So they're just named categories of functions with given properties. That's a very 30,000 foot, really it's a 60,000 foot level way of thinking of Sobolev spaces. But that's a crucial element of nearly every known attempted proof or counterexample of the Navier-Stokes problem. On the other hand, you have the practical application side. You can prove over here that a solution can exist in theory, and here's what category of mathematical expression it belongs to. On the other hand, you have here's what the exact solution looks like as a written mathematical formula. The former is what a mathematician would understand as solving Navier-Stokes, and then the latter would be what an engineer or a physicist would understand as solving Navier-Stokes. There's also a critical nuance I want to make the public aware of as well, if they're not aware of it already. There's a Navier-Stokes problem with the indefinite article, and then there's the Navier-Stokes problem with the definite article. A Navier-Stokes problem is any problem involving Navier-Stokes, as the name would imply. The Navier-Stokes problem usually refers to the Clay Mathematics Institute Millennium Prize problem, which in PDE speak refers to the Cauchy problem, which is infinite domain. You're solving for the velocity and pressure fields of a flow problem involving an infinitely wide and infinitely deep ocean where the initial condition has derivatives of all orders well defined, and it's also square integrable, which in fluids speak means it conserves kinetic energy. Makes sense. Has to be perfectly smooth as a mathematical function, and it also has to simulate a velocity field that is observed to conserve kinetic energy. Does the flow stay that way forever, or is there ever a point where it stops having those criteria? That's what the Clay Mathematics Institute Millennium Problem asks. Is that a yes or a no? In other words, it's a proof of yes and a counterexample of no. The official problem statement written by Charles Pfefferman lays all this out in graphic detail. Terence Tao has shown famously that the answer is no. The equations do not always hold together for overall space and all time. If you average and put a little fuzzy, some stochastic averaging to tame a little bit of the nonlinearity in the nonlinear advective terms. So if you're going to show that they do hold together, you can't average them, or you can't average them as much. So that's what Tao did. And now Dr. Tao is the greatest mathematician in the world. And the only person that can hold a candle to Tao that I know of are people like Perelman or Martin Hare who just ran the KPZ equation through the ringer in a preprint that I found highly elegant in so many ways. Hare is a brilliant mathematician, I'm telling you. Uh, you should, I think anybody interested in PDE theory, especially the stochastic variety, should absolutely read Hare's paper on solving the KPZ equation. Amazing paper. But regardless of who did what, I think what makes my work different, as grandiose as many are going to call me for that, for saying something like that, in the presence of such renowned names here that I've quoted here. I think what makes my work a contribution, just a contribution. No, I'm not claiming to be some misunderstood genius here. I'm not saying that. There's been a lot of people, I'm sure, who were calling me that, but I'm not. I'm telling you, I'm not that. That's not what's going on here. I believe I've made a contribution to the discussion about Navier-Stokes. If I've solved it, well and good. But if not, at least I've made a contribution. It is what makes mine different from what has been done before is the fact that I'm not using energy inequalities to prove whether there exists a Sobolev space of satisfactory velocity fields. Instead, I'm taking the equation and deriving the written form of the velocity field, and I'm showing. Then I'm starting to talk about Sobolev. So then I'm going to show, okay, here's what Sobolev space that would have to be a part of in order for this formula to work. If this formula is the formula, then what Sobolev space is that a part of, and then does that match up with anything the Clay Institute would want in the infinite domain case? It's kind of a backdoor approach to how it's usually done. Usually, the way Navier-Stokes handles conservation of energy, when you especially when you get into Lattice-Sykes inequality and the Gagliardo-Nierenberg interpolation inequality, that's where you get into. That's what a lot of people have been kind of working around, near, and in. Otelbev, I think I'm pronouncing his name correctly. He's known for having one wrong formula that made his proof go kaflooey, but he did. He really just punched his fists off with those energy inequalities. Essentially, he was saying, okay, if Navier-Stokes conserves energy, if we work on that assumption, how does it conserve energy when you tear it all the way down to the raw velocity field? And does that match up with square integrability, and does that allow any velocity field that is anything less than C infinity smooth? That's the question. That's the way a lot of people have been approaching the problem. I've been approaching it somewhat backwards. Number one, naively solve it as though it were always right, and then once you've assumed that such a formula exists, is there a way in which that formula would be able to work? I'm sorry. Is there a way in which that formula can blow up, can become undefined in the presence of a perfectly smooth square integrable initial velocity and boundary velocity if there's a boundary? So it's like saying, well, I tend to have a bit more naive approach. But the naivety, I believe, is justified because, number one, engineers, like I said, on one hand, engineers need a formula. Mathematicians need a Sobolev space. I think it's good to have both because I think a true closed form PDE solution that is mathematically watertight, no pun intended, should have this looked at from a Sobolev perspective and a written formula perspective. Can you find the Sobolev space of the written formula, and can you prove that written formula lies in that Sobolev? It's like you need to have the functional analysis side and the functional form side. Can you write down a formula and then prove that formula is of the same category as what we kind of want it to be? Is that possible for it to be the way we want it to be, or are there exceptions to the rule? That's what we're really trying to figure out. Now, why C infinity and why L2 square integrability? Because that's what makes a fluid flow physical. That's what we observe fluids to generally follow. Now, I'm not saying they always follow C infinity in like a real flow situation, but Navier-Stokes is itself an approximation. It assumes Galilean invariant stress. The constitutive equation is linear. The constitutive equation for stress that goes into Navier-Stokes is a linear one. We're assuming Galilean invariance. So that and a few other facts have a lot of implications for why C infinity is what we picked. It's also because C infinity is an inherently mathematically stable solid space. If something is C infinity, then the issue of smoothness or the issue of differentiability is not going to be what blows it up. If it's square integrability, then that means that conservation of energy is not violated. It can't ever fail to conserve kinetic energy regardless of how turbulent it gets. So that essentially is to say there's no other structure that would cause it to fail in the way we understand the equations to simulate physical reality. But I think we've gotten a little too lost in the weeds here once again. I think what will help is some videos of how this is all put together and some plots that I'll be creating in the coming weeks. That I think will help spur discussion. That I believe will help kind of get people talking about this a little bit more. For those of you on YouTube, thank you for your support, and I hope there will be much clarity on this for years to come, if I'm correct. For those of you on Reddit, I know Reddit's kind of a mess. We all know that. But because you're talking about something that hasn't had a whole lot of discussion yet, I think it would help everyone if you took the focus off of me and put the focus onto the math. So, yeah. Those of you on LinkedIn, I have 2 words to say to you. Thank you. Actually, 5 words. The other 3 are I love you. There are so many people who have helped me in every way. I'd like to thank my family and my friends for all those late night conversations. So often I've had my head in my hands wondering, is this ever going to get done? 7 years of all-nighters and so many late night runs to the 7-Eleven for some electrolyte. So much wondering over whether I'll feel like I look good again with my weight going down to 160. Doesn't look very good on 6-0. But after the equations were done, I gained 20 pounds very quickly, and I'm still able to do my push-up sets and all that. I found ways to eat even better than I've been eating, and I no longer need to eat 4,000 calories a day. I no longer have to say no to friends who want to hang out. It's been wonderful since the equations were since I solved this to a satisfactory degree. I think things have my life has become much more stable and much more steady since this, what seemed like and what felt like a never-ending war, finally came to an end. And now that I'm in what many might call the cleanup stage, I have the time and the ability now to reflect on my experience and reflect on what it was like to strive against a formula you could write on the size of an index card for for almost a decade. Why would like the question of why would a man trade his 20s for a math problem is bewildering to many, and I acknowledge that completely. And I want to also use some of this time in this series to show the various things I tried in solving it and how I arrived at the framework I arrived at. That's a lot of work to show. So I'm going to need some time to think about how I'm going to show all this out because it is complicated. But I have given a lot of thought to the matter, and I believe it is worth the community's best interest for me to make some explanatory tutorial videos on how I did this and how we ought to use it. As for the clay problem, I will have to present that somewhere. It might be another conference, or it might not be. It might be right here on YouTube. That might actually help because conferences are a high stakes event. And they're a high logistics event too. And for many, they're a high cost event. What that means is I want to use that wisely. Usually, when I'm in a conference, I'm in front of industry people. And that means that I'd rather be presenting the bounded flow, which is more pertinent to practical problems that they can use that to solve. Now, when it comes to the clay problem, that is where I think things are going to become a little bit less practical and more towards the theoretical side. And I think this is a good place for that. So I think what I should do also is to make a 30,000 foot level view presentation of the clay problem solution. And because again, in the paper, you can see right when the section of right when the MCH lift, the theta of phi, when that function is written down in full, it was a second order linear ODE, and it had a particular solution and a complementary solution. The complementary solution that leads to the clay problem solution, which involved a Lambert W function and a homotopy and a few other things too. Whereas the bounded flow, that was the particular solution of said ODE, and that led to the quartic hash that led to the dueling quartic situation, the alpha and beta functions that we saw. So the fact is, it is a complicated proof. But I think it would be good for me to articulate the exact structure of things, because the clay side and the bounded side, or should I say the unbounded side and the bounded side, those are both in the same paper. And in the beginning, there's the philosophy of the paper, and then in the middle, there's the bounded flow, and in the end, there's the unbounded clay problem section. So it's really broken up into 3 sections. And I think it would help if I also integrated a situation. I should implement a part of this series that'll show how the paper is structured and how to read the paper, because it is complicated. Now, if any of you have any suggestions for how I can make this any easier for the community to digest, please let me know in the comment section below, and just let me know what you'd like to see. I'm taking feedback from the community. If you woke up tomorrow and I had made just the perfect Navier-Stokes video series, or I started to anyway, what would you want to see in it? I want to take feedback from you before I even sit down and begin. What do you want to see? What do you want to see that I can factor into a video, that I can put into a video series? What do you want this to look like? Do you have a preference? Or do you want me to figure this out? Because I can do either one. But if one is going to add more value to the mathematics and engineering communities, I'd like to do that one. So if anybody has any constructive criticism about the paper or about the proposal for the series, I'm open to hearing any kind of feedback. That's not to say I'm asking anybody permission. Don't frame it that way. I'm just asking, is there a way that it would work the best if I did it that way? Because I'm not sinking hundreds of hours into a video series if it's not going to help anybody understand what they want to understand about this. That'll be a waste of my time and an assumed waste of yours, both of which are not good for the flourishing of civilization, which is what I, as an engineer, must do. That's what I'm ethically bound to be doing here. So, with that said, I hope you all have a wonderful day tomorrow or whenever. And as always, thank you for visiting my channel. And thank you for visiting my research. And I hope I'll get to meet so many of you guys and hear about your research and what you're doing in life and all the stuff you're doing here. And just, I hope to have great, clarifying, fortifying conversations with people in this field. Math is fascinating, and so is physics, and so is engineering. And I really am looking forward to seeing where these kinds of things are going to go. So, thanks for watching. Thanks for hearing me out. And I will see you soon. Peace.